Hi everyone, my name is Yasser Shoukry. I am from UCLA. I'm going to talk about my poster on dynamical systems under sensors attacks. So suppose you have a dynamical system like a car or an aeroplane or whatever, some adversarial attack come and malfunction some of your sensors. This attack is this information is going to propagate all the way to your controller, and the controller is going to take wrong action. This problem is not theoretic. Actually, we implemented such an attack. Here I am going to show you this module we implemented on our lab at UCLA. This module you can go and implement it on a car. Actually, if you went to your car and behind the wheels, this is the ABS sensor that is used to brake the cars. Just put the module there and activate it, and it will work for 5 days. Then what happens is when you start pressing the brakes, the car, instead of parking, it will skid over and turn away, and we showed some experiments showing the effectiveness of this attack. So the problem setup right now, you have a dynamical system. You can model it here right now as a linear dynamical system. You have a states, for example, the speed and the position of your car evolving through this dynamics. And now you have your outputs like the sensor, the ABS sensor or whatever is measuring some of the states, and you have some noise, and then someone comes and attack your sensors. The assumption that we have over here, that the attack is sparse. This means that he cannot attack all of the sensors. He can attack some of your sensors. So we model this the attack as a sparse signal, and our objective is to estimate the state of the state of the system as well as this sparse signal. We can model the problem as L0 minimization. Since we have here a sparse signal, we can relax it to LR L2 minimization and whatsoever. The problem with these techniques that you need conditions like the restricted isometry property or the restricted eigenvalues. In the normal information theoretic literature, you have the opportunity to choose the observation matrix such that this RIP condition is satisfied. When you have a dynamical system, you cannot change how the sensors are measuring the states. You don't have an influence to choose this observation matrix such that it satisfies the problem. So we would like to have a new paradigm that gets rid of the RIP or the restricted eigenvalue properties. And here, that's what we use, a satisfiability modulo theory. The satisfiability modulo theory approach, or the SMT, you have a formula that have both Boolean variables as well as non-Boolean variables, and you try to satisfy this formula. This is the formula that we would like to satisfy. We are searching for BIs and X. The BI is an indicator variable saying whether this sensor is under attack or not, and the X is the state of your system. And we would like to satisfy these conditions over here. Whenever BI is assigned to 0, this means this sensor is not under attack. Then the error between your the measurements you have and your estimated state needs to be bounded away by the norm of your noise. These have to be satisfied for all your sensors, and then you have here a bound on the number of sensors that can be under attack, which we call here S bar. We would like to find B's and X's that satisfy this formula over here. Unfortunately, there is no SMT that can solve this particular problem, so we have to come up with our new SMT solver, and that's what we have here over this slide. Any SMT solver has an underlying set solver that try to reason about the Boolean variables. We have here theory solvers and countermeasure based search that trying to reason about the non-Boolean variables and try to assign them. And we implemented this SMT solver, and here is our theoretical results, saying that whenever the attack, the energy in your attack is bounded away by these variables over here, then our SMT solver is always going to detect such an attack. Suppose that the attacker comes and put a very small attack that is comparable to the noise level. Then we have another theorem saying that how much is the estimation error is going to be bounded. And here, just to show how our SMT solver scales, I'm going just to point for this plot over here. Here we are scaling, we are changing the number of sensors from 3 up to 150 sensors. 1/3 of these sensors are under attack. We can see the blue line is how our SMT solver is scaling versus an LR L2 minimization and versus an L0 L2 minimization, which is the brown and the black over here. Thank you.